February 3rd, I think. This is a problem that's out of our textbook, and I find it quite interesting. It's on page 55 of the textbook, and it's problem 38, and it's a problem that one of you asked about this morning, and I gave an overview of it, but let's actually go through and solve it now. So here's the situation. It's a mixing problem, but this time we're cascading the mixing. And so I have a 100-gallon tank that's full. It's got 100 gallons in it. And I've got a 200-gallon tank, and that one's also full. It has 200 gallons in it. I'm pouring pure water into this first tank at 5 gallons per minute. And I'm taking it out at 5 gallons per minute. So the 100 gallons of liquid in the tank stays 100 gallons all the time. And something very similar is happening down here. I'm taking water out of tank 1 and putting it into tank 2. It comes out of tank 1 at 5 gallons per minute, and so it goes into, the input into tank 2 is water at 5 gallons per minute. Now it's not pure water, it's a brine, because the tank 1 initially, this is an initial condition, had 50 pounds of salt in it. 50 pounds of salt dissolved in 100 gallons of water. So it's not pure water that comes out, it's a brine. And tank 2 initially also had 50 pounds of salt dissolved in it. That's an initial condition. Y of 0 is equal to 50 pounds of salt. And it's 5 gallons per minute in to tank 2 and 5 gallons per minute out. And so it maintains its 200-gallon content, but the concentration and the amount of salt in the tank changes from time to time. Let's let x of t be the amount of salt in tank 1, and y of t can be the amount of salt in tank 2 at time t, of course. And the first part of the problem is to find x of t and y of t. So for these kinds of problems, the change in x is going to be salt in minus salt out. That's the change in x. It's salt in minus salt out. Now what would salt in be? Well, liquid's coming in at 5 gallons per minute, and in that liquid the concentration of salt is, well, it says it's pure water, so it's 0 pounds of salt per gallon, which makes the N just 0. And the salt out, well, liquid's coming out at 5 gallons per minute. And what's the concentration? Because it's the concentration that I have to multiply by. This was the concentration here. It was a 0, but it was still the concentration. Well, the concentration would be, by definition, would be how much salt was in the tank at that time. This would be x of t. I'm just not writing the t right now. The amount of salt in the tank divided by the volume of water in the tank. And that was given in the problem as 100. And so this would equal x over 20, if we want to write it that way, because 5 into 100 is 20. So x over 20, that's the salt out. So that tells me then that x prime is equal to n minus out. And that's my first differential equation. And this is a variables separable differential equation. And let's scroll down just a little bit, and we would write this as 1 over x dx is equal to negative 1 over 20 dt. And then to solve, I'd integrate both sides, and that would give me natural log x is equal to negative 1 over 20 t, and I think I'll just put the t up here, plus a constant. But we don't want log x, we want x, and so we'll exponentiate, and when I do that, we'll get x is equal to e to the negative t over 20 plus c, which would be e to the negative t over 20, e to the c, because when you multiply two bases raised to powers, but the base is the same, you add the exponents. So if I multiply these together, I get that back. Now c is an arbitrary constant, and so e to the c would be an arbitrary constant. And so finally, for convenience and by convention, I would write this as c e to the negative t over 20. So let's record out here that my x, which is a function of t, is equal to c e to the negative t over 20. But we have an initial condition, x of 0 is equal to 50. So from the initial condition, I find that x of 0 is 50, so this would be 50 is equal to c, and then e to the what? E to the 0, negative 0 over 20, that's e to the 0 is 1, and so that would be e to the 0, which is a 1, and I see that c is equal to 50. So finally we'll write x of t is equal to 50 e to the negative t over 20. And that's how much salt in pounds is in the first tank. Now let's think about the second tank. Let's get a different color for two-tank thinking here. So this is going to be about y of t. So y of t will change according to salt in minus salt out. And salt in, well, we're getting 5 gallons per minute, but what's the concentration? The concentration would be however much salt is in tank 1 at a given time divided by the volume of tank 1. So there's salt in, which would be 5x over 100, or x over 20 would be salt in. Now what about salt out? Well, salt out, it's coming out at 5 gallons per minute, and the concentration would be however much salt is in tank T divided by the volume of tank T would be 200, would be y over, and this would be y over 40. So we have found that y prime is equal to salt in minus salt out would be x over 20 minus y over 40, and I'm going to transpose this term, and I guess I'll write it right down here. Y prime plus y over 40 is equal to x over 20, but let's not write that as x, because I know what x is. I know that x is 50 e to the negative t over 20. So I'm going to write this as 1 over 20, and in place of x, I'm going to say 50 e to the negative t over 20. And then let's clean it up right now. We'll clean it up, and we'll get a y prime plus 1 over 40 y is equal to I think I'll just leave this 5 halves. 5 halves e to the negative t over 20. That looks pretty good. All right, well, then we found out what y prime is. Now let's look at this. We don't know what y is yet, but we know that this is a differential equation that defines y prime. And look at that. This is a linear first order ordinary differential equation. So we've got a procedure for solving this type of equation. And the procedure is we would find rho of t, that would be our first step. That's an integrating factor. And this would be e to the integral, and then p of t would be the canonical form here. That would be the coefficient function of y. So this would be 1 over 40. And that would be dt would be e to the t by 40. And we can, it's an indefinite integral, so, you know, plus c, but we can take that c to be 0 and then use as an integrating factor e to the t over 40. Now what do we do with an integrating factor? Well, we take the differential equation, and we're going to use the differential equation in this form right here, and we're going to multiply that by the integrating factor. So I get an e to the t over 40 y prime, remember I'm multiplying right here by the integrating factor, plus 1 over 40 e to the t over 40. Sure, that looks like a t. E to the t over 40. Y is equal to 5 halves. I'm going to go ahead and write this e down. E to the negative t over 20, and then I've got to multiply by this one. E to the t over 40. Now let's clean that up. First thing to do is to see that over here I've got an expression that looks like it could be the derivative with respect to t of e to the t over 40 y. That was bothering me. You see, this would have been y prime times e over 40, so really I've got a little prime there, and now this is all correct. So it is that in fact is the derivative of this product what I have for left hand side here. Let's just check it real quick. First times the derivative of the second, yeah, that checks out, plus the second, there's the y, times the derivative of the first, that would be 1 over 40 e to the t over 40. By gosh, that's right. And so what I wrote there is good. And then this one's going to be 5 over 2, and this would be e to the negative t over 20. When I multiply these bases, the bases are the same, so I'd add here, get a common denominator. This would be negative 2 t over 40, and a positive t over 40 would be a negative t over 40. So this would be e to the negative t over 40. And I'm just going to throw a comma in here. Now the next thing we do is integrate, but the integral with respect to t of the derivative of this function, this is the derivative with respect to t, would just be e to the t over 40 y. And that would be equal to, and here I'm going to have to integrate, but it's going to be a 5 over 2 integral e to the negative t over 40 dt. Now we're going to do an integration by substitution. if we want to think of this as e to the u, what would du be? Well, du would be negative 1 over 40 dt. So I'd need a negative 1 over 40 in here to go with the dt, and I would have to pay for that by putting a negative 40 out here. And now I can integrate that. It's a simple form. I lost my cursor. Cursor, come back. So I'm going to take this and jump over here, and I'd have an e to the t over 40 is equal to, now this is 5 over 2 times negative 40 would be negative 20, and 5 times negative 20 would be negative 100. And with this 1 over 40 dt, this is e to the u du, so the integral would be e to the negative t over 40, and then of course it would be plus a constant. So I'm going to put a comma in here and work linearly for a minute. And I copied that down, and for some reason I left off the y. So now that's correct. Now let's divide by the coefficient of y, and we get y is equal to negative 100. And then what would this be? This would be e to the negative t over 40 over t over e to the t over 40 would be e to the negative 2t over 40, which would be an e to the negative, instead of 2t over 40, I'm going to say t over 20, and then plus c, and I'd be dividing by e to the t over 40, so that would give me a negative t over 40 if I write it in the numerator. Almost done. Remember, we've got an initial condition that y of 0 was 50 pounds of salt, and so using that initial condition, I would have that 50 was equal to negative 100, and then this would be a 1, wouldn't it, because t is 0, so that would just be a 1 plus c times, and well, that would be a 1 also, so c times 1, or transpose here, c is equal to 150, that would be pounds, or y of t, now we're closing in on it, is this would be 150. I'm going to write the positive term first. E to the negative t over 40 minus 100 e to the negative t over 20. And that is y of t. And somewhere up toward the top, we've got x of t, which was equal to, I wrote it down here, was equal to 50 e to the negative t over 20. So that's the first two pieces. The last piece was to figure out the max amount of salt ever in tank 2, but you've got an expression for y of t, so you just use min-max theory from calculus 2. Take the derivative of y, find the partition points, see if they're in the domain of y. That'll give you critical points, and then use a second derivative test or the first derivative test on the critical points to find if the critical points are relative max, relative min, or in fact neither, and you would be looking for the relative max, and so I'll let you do that. So that's a nice little problem, and I'm happy to have been able to work it for you. Thank you, and have a good afternoon, evening, morning, whatever, depending upon when you watch this. Thank you.